So chapter 3 is, uh, am I audible?
Yes,
Yes,
ma'am.
ma'am.
Chapter 3 is on Nyquist stability criterion, and you can see that Nyquist stability criterion is basically a frequency domain based stability criterion. Now, already we have studied Hurwitz stability criterion as well as route stability criterion. Now, those two stability criteria are complex domain based criteria because first we'll have to form the characteristic equation. That means we must know the characteristic equation of a given system, then only we can apply either route stability criterion or Hurwitz stability criterion. That's why those two are complex domain based or is domain based stability criterion. The disadvantage of Route Hurwitz criteria is that with the help of those two, we can only find the absolute stability. We can get information about the absolute stability of the system. Next, we have studied another tool, which is basically an analysis and design tool. And as a part of analysis, with the help of the name of the tool is obviously root locus technique, and we know that with the help of root locus technique, also we can find out the stability of the system. We can find out, we can ascertain whether the fact that whether a system is stable or not, right? And also we can find out the conditional stability of the system with respect to a variable parameter of the system. That means if I take the plain and simple case of forward path gain k, then for which range of gain k the system will remain stable if the system is not absolutely stable. And also we can find out with the help of root locus technique, we can find out relative stability of the system. But the difficulty of root locus system is that yes, we will have to find out the locations of the roots on the S-plane, though we can apply several simple rules for constructing an approximate root locus. But if you want to have a sketch or have an accurate sketch, then accurate root locus sketch, then actually the method should be the we'll have to solve the characteristic equation repeatedly for different values of the variable parameter of the system. Right? Now, in contrast, this Nyquist stability criterion, as I said, is a frequency domain based stability criterion, right? And the advantages in this for applying this particular tool, that means Nyquist stability criterion, it's not required to find out the characteristic equation of the system, and it's not needed to solve the characteristic equation for finding out the locations of the roots of the characteristic equation, or in other words, the closed loop poles, locations of the closed loop poles of the system on the S plane. Okay. It's a graphical tool, that is another advantage. And the main advantage is that simply from the open loop frequency response, from the, I repeat, from the open loop frequency response, we can ascertain the stability, be it absolute stability, be it conditional stability, or be it relative stability of a given LTI system when the feedback path will be closed. That means the if we know the open loop transfer function, try to recall the experiment identification of linear system using frequency response test. So what we did in that particular experiment, using frequency response test, we actually obtained the open loop transfer function of the system. Am I right?
Yes, ma'am.
Yes, ma'am.
So actually, we did obtain GSHs, which can be called either the open loop transfer function or the open loop frequency response. So when we'll be closing the feedback path, that means the closed loop system will obtain a closed loop system. And now we know that we are really bothered or concerned about the stability of the closed loop system. Okay. So from the open loop frequency response, we can find out the stability of the closed loop system. So that's why the tool is very simple. Very easily we can construct the required graphical plot or required graph, whatever, we'll see what is that, and we can apply Nyquist stability criterion. Now, Nyquist stability criterion, you can see somewhere it's written here. Yes, you can see that Nyquist stability criterion is based on a theorem of complex variable, and the theorem was proposed by Cauchy, right? And the name of the theorem is principle of argument. Principle of argument, right? It's a theorem of complex variables. Now, Nyquist stability criterion completely rests on this particular theorem. So, before we learn Nyquist stability criterion, we'll have to learn principle of argument, that is our mathematical preliminaries. Now, let us consider a function QS. Now, this function QS, this function QS is not the characteristic equation of a system. It's an arbitrary function, but it's a function of ace, where ace is a complex number and ace is given by sigma plus j omega, right? Any function of ace, right? So again, I repeat, QS is not in this particular expression. QS is not any characteristic equation for a given LTI system. Now, here you see QS has been expressed as a quotient of two polynomials. The numerator polynomial, both the polynomials are expressed in factored form. The numerator polynomial is given by s minus alpha 1 into s minus alpha 2 dot s minus alpha n. And the denominator polynomial is given by s minus beta 1, s minus beta 2, s minus beta n, right? So again, I repeat, QS is function of ace, where ace is a complex variable. And for this particular function QS, if we apply our knowledge of poles and zeros, just try to recall the definitions of pole and zero for a particular function, then we'll find that all these alphas are the zeros of this function QS, and all these betas are the poles of this function QS. Am I right?
Yes, ma'am.
Yes, ma'am.
Now, let's take a particular value of ace, right? And let it be, say, S0. So if at s equal to s0, s0 is a point on the s plane because s is our complex variable given by sigma plus j omega, and we are familiar with s plane. Okay. So let's take a point s0, and if you assume that at s equal to s0, at that particular point on the s plane, qs does exist, QS does exist, then we can say that QS is analytic at a point s equal to s0. Do you agree?
Ma'am, would you repeat?
Let's take any arbitrary point on s plane, say s equal to s0.
Okay.
Okay. Now, if we assume that at that particular point s equal to s0, we can put the value of s0 in this expression and we can compute QS. Yes
Yes.
or no? Right?
Yes.
So when we'll get value of QS, if at s equal to s0 this function QS exists, then only we'll get a value of QS,
Yes.
right?
Yes.
So we can say that at s equal to s0, if the value of this function, or if the function in general, if the function exists, then we can say that QS is analytic at that particular point.
Yes.
I guess you have heard this term.
Yes.
Or in other words, we can say that S0 is not a singular point for this QS.
Yes.
The singular points will be
Beta 1, beta 2.
beta 1, beta 2, beta n, where
Yes.
QS does not QS and its higher derivatives does not higher derivatives do not exist, right?
Yes.
Okay, so that means if we take a point on the S plane at which QS is analytic, then we'll get a value for QS.
Yes.
Now, since S is a complex variable and Q is function of S, hence QS will also be a complex one. Yes or no?
Yes, ma'am.
So, since Q is a function of S and S is complex in nature, hence QS for a particular value of S where QS is analytic will also be complex. So for that particular value of S, let's assume that QS is complex and is given by U plus JV. QS is U plus JV, right? Do you agree or
Yes,
not?
ma'am. Yes.
So QS can be represented as U plus JV. So already we are familiar with S plane. This is our S plane and the axes are sigma and j omega. So suppose some QS is given and at S equal to S1, at S equal to S1, QS is analytic. Hence we'll get a value QS1. Agree?
Yes, ma'am.
So we can conceive another plane which we'll call QS plane. QS plane, and it is level the axis as U plus J, sorry, U and JV, right? So at S equal to S1, if the given QS is analytic, then we'll get a point on this QS plane which will be QS1. Have you understood this? Have you understood this? Hello?
Yes, ma'am.
Is it absolutely clear? Is it absolutely clear to everyone? If required, I can repeat.
No, ma'am. I think clear.
Okay. So we can assume that for S equal to S1, QS exists. So we'll get QS1, which will be given by some U1 plus JV1, and hence we can map the corresponding point on the QS plane for which the axes are leveled as U and JV, right? So QS is the mapping function. The given function QS is the mapping function with the help of which a point on the S plane where the QS is analytic can be mapped onto a point on the QS plane. Clear?
Yes, ma'am.
Okay. Now, now let's take a closed contour. That means a closed curve, a closed contour on the S plane like this. You can see the closed curve. So we call it a contour, a closed contour on the S plane, arbitrary contour. Okay, but there is one condition that this particular contour that we are considering on the S plane will not pass through any singular point for the given QS, for the given function. So the contour will not pass through any singular point for this QS, or in other words, at all the points on this closed curve, at all the points on this contour, QS will be analytic. That means if we consider any point on this closed curve or closed contour, will get a value of QS having a magnitude and a phase angle. Clear? Since QS is complex. Clear? Have you understood this?
Yes,
Is
ma'am.
it clear? So let this contour be such a contour for the given QS, right? So now let's learn one convention. Now we'll traverse along this contour. We'll traverse along this contour in clockwise direction. Follow this cursor. I'm moving along this contour in a clockwise direction. This is the clockwise direction, right? So I'm moving along this contour in a clockwise direction, and in the process, I'm identifying or marking the area lying to the right of the contour. This region, if I move along this contour in clockwise direction, then this area will lie to the right of this contour. Clear? Is it clear?
Yes, ma'am.
Similarly, while I'll be moving in this particular direction, then this area will lie to the right of this contour. Okay, so we'll traverse along this contour on the S plane, along this closed contour on the S plane in clockwise direction, and in the process will shed the region lying to the right of this contour. So this is the region, and this region will say to be enclosed by this, right? And this regions are lying to the left of the contour while we are traversing in the clockwise direction. Hence, this region will not will not be enclosed by this contour. Have you understood this? Have you understood this?
Yes, ma'am.
Okay. So this is the convention that we control system engineers follow. Mathematicians follow a different convention, right? In some books, you might get that convention, but ultimate result is same. What is the convention? Convention is will traverse the contour in counterclockwise direction, and in the process will mark the region, will identify the region lying to the left of the contour. Clear? The region will be same. So in this course, I'll follow the first convention. That means we'll traverse the contour in clockwise direction and we'll identify the region, we'll shed the region lying to the right of the contour, and that region will said to be enclosed by the contour. Okay. Now, so far is this clear? If you have any doubt, please feel free to ask. So far is this clear?
Yes, ma'am.
Yes, ma'am. Clear.
Okay. Now you see, since it's a closed curve, so we are starting from this particular, say, we are starting from this particular point S1. So while traversing along this contour, the next point is S2, S3, S4, S5, and the final point will again be S1 since it's a closed contour, right?
Yes, ma'am.
So the first point and the final point will be same since it's a closed contour. So for S1, since the contour doesn't pass through any singular point for the given QS, hence for S1 on the QS plane, we'll get a point QS1. For S2, we'll get a point QS2. For S3, we'll get a point QS3. For S4, we'll get a point QS4, right? And finally, again, since the last point is again S1, hence we'll get QS1. So what does it imply? If we traverse along a closed contour on the S plane, which does not pass through any singular point for the given QS, on the QS plane, again we'll get a closed contour. Have you understood this?
Yes, ma'am.
Okay. Now, the contours are generally denoted by the symbol tau, right? So, the QS plane contour, generally we call this QS plane contour a tau q contour. We denote this contour as tau q. Yes. Can you see this tau q? So, tau q denotes QS plane contour. Okay. Now, for any point S1 at which QS is analytic, we can find out, since QS again will be, or QS1 will be a complex one, hence QS1 will have a magnitude and a phase angle, right? So the magnitude of QS will be equal to magnitude S minus alpha 1, or this phasor length S minus alpha 2 multiplied by the phasor length of this, so and so forth. And in the denominator, we'll get magnitude S minus beta 1 mod S minus beta 2, so and so forth, right?
Yes, ma'am.
So this equation will give us the magnitude of QS. And what about the phase angle of QS at a point? For a point is equal to S1, the phase angle will be given by Q angle QS will be equal to summation of the angles contributed by the zeros, and the angles contributed by the zeros will be positive since the zeros are present the numerator, and minus the summation of the angles contributed by all the poles, right? But the angle contribution of each pole will be negative. So angle of QS can be represented as angle S minus alpha 1 plus angle S minus alpha 2 plus dot 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 minus S minus beta 1 minus S minus beta 2, etc. Right? So for A is equal to S1, if I consider again this S1 to be the starting point, so for A is equal to S1, the angle will be Q angle QS1 will be equal to angle S1 minus alpha 1 plus angle S1 minus alpha 2 plus dot 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 minus angle S1 minus beta 1 minus angle S1 minus beta 2, so on and so forth. And similarly, replacing this A's by S1, S1 will be some sigma 1 plus j omega 1. So replacing S by sigma 1 plus j omega 1, we can obtain the magnitude of QS. Clear?
Yes, ma'am.
Now, for Nyquist, for applying Nyquist stability criterion, right? Actually, we'll see that number one, what is going to be the shape of the contour on the QS plane, closed contour on the QS plane. The shape will be influenced by the magnitude of QS, by the magnitude of QS, as S will vary from S1 to S2 to S3, S4 on the S plane contour. Do you agree? Do you agree?
Yes, ma'am.
Yeah, ma'am.
On the QS plane, you see this is one QS vector. This is one QS vector, right? So the length, this phasor length, this phasor length will be influenced by this equation. Now we'll see that we are not really concerned about the actual shape of the QS plane contour, right? The actual shape of QS plane contour will not be required for applying Nyquist stability criterion, right? What is important to us? The important factor is whether this QS plane contour tau q is enclosing the origin of the QS plane or not. So we are only concerned about the fact that whether the QS plane contour, the QS plane contour corresponding to the S plane contour on the S plane does encircle the origin of the QS plane or not, right? So we'll try to find out whether the closed contour that we are getting on the QS plane for a closed contour that we have taken on the S plane encloses the origin of the QS plane or not. So for that, the this equation, angle contribution by the zeros and poles of QS plane will be required. Now, let us assume that we have taken a contour on the S plane. Let's consider this particular figure. So let us assume that on the S plane we have taken a closed contour, right? S plane contour for a given QS, for a given QS, and the condition is this closed contour on the S plane does not pass through any singular point for the given QS. Clear? Clear?
Yes, ma'am.
Okay. Now let us assume that we have taken a contour on the S plane in such a manner that the contour encloses 1 0 of QS. What was our QS? This is our QS. S minus alpha 1, S minus alpha 2, etc. Okay. So it's clear from this figure that this closed contour on the S plane encloses. This is the region which will be enclosed by this contour because we'll traverse the contour in the clockwise direction. So this is the region being enclosed by this contour, right? And from the figure, it's clear that 1 0 of QS is being enclosed by the S-plane contour, while rest of the zeros and poles of QS are lying in a region which is not enclosed by this S-plane contour. Is it clear? Only one single zero of QS is enclosed by the QS plane. Sorry, S plane contour. Clear?
Yes, ma'am.
Okay. So suppose we start from this particular point. Let's assume that this is our starting point on the S-plane contour. So let's construct the phases. So this is, if we call it S or S0. So this is the phasor S0 minus alpha 1. This is the phasor S0 minus alpha 2. This is the phasor. In this particular, while I'm explaining this particular diagram, I'm not considering, otherwise I'm not considering the signs over here, because you might find that these two zeros are lying in the right half of the S plane, whereas these poles are lying in the left half of the S plane. So this phasor should read as S plus beta 1. I'm not considering, okay, that fact. Just in general, all the phases are being depicted as S minus alpha 1, S minus alpha 2, S minus beta 1, S minus beta 2, S minus beta 3, so on and so forth. Clear?
Yes, ma'am.
So automatically, if the value of beta is negative, the sign will reverse. Will be reversed. Okay. Now let us consider this phasor. This phasor. So as we'll move along this contour in the clockwise direction, this phasor will move like this. Can you follow the cursor? You understand this? And ultimately, the final position of the phasor will be like this. Yes or no?
Yes, ma'am.
Okay. So what will be the net angle change by this phasor? Change in angle? Because you see, that was the starting point, right? So when the point has been shifted to this point, so the phasor has changed, the phasor length is changed. I'm talking about this particular phasor. The phasor length has changed, as well as the phase angle contribution of this phasor is also changed, right? Yes or no?
Yes, ma'am.
Yes, ma'am.
Right? Already we have discussed that we are not interested about the length of the phasor. We are only interested about the angles. So as the phasor will move, as will traverse along this closed contour, the phasor will also, the tip of the phasor, to be more precise, the tip of the phasor will also move along this contour, and in the process, the phasor will undergo a net change in angle. Yes or no? Yes or no?
Yes, ma'am.
So what will be the net change in angle of this phasor as we move along this contour?
Minus 2 pi.
I'm talking about this phasor. This phasor will move like this.
0.
So which one is the correct answer? Minus 2 pi or
Zero.
0?
Zero. Zero.
Sure,
Yes, ma'am.
sure. Okay. So let me get back to this equation. So we are trying to find out now delta QS, net change in angle. So for beta 1, we have seen that delta QS will be equal to delta angle S minus alpha 1 plus delta angle S minus alpha 2 plus dot 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 minus delta angle S minus beta 1 minus delta angle S minus beta 2. Do you want to write down this equation? Will that help? Are you writing down the equation?
Yes, ma'am.
So the equation will be, you see, delta QS. The left hand side, we are trying to find out net change in angle of QS phasor. So delta QS, left hand side, naturally the right hand side will be delta angle S minus alpha 1 plus delta angle S minus alpha 2 plus dot 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 minus delta angle S minus beta 1 minus delta angle S minus beta 2.
Ma'am, please repeat. That is delta angle of QS, right?
Hmm. Net
Okay,
change in
okay,
angle.
okay, okay.
I say,
Yes, ma'am.
okay. So for this particular phasor, S minus beta 1, we have seen that delta S minus beta 1 is 0. Net change in angle after traversing this close contour completely. Net change in angle of this phasor is 0. Yes or no?
Yes, ma'am.
So
Yes, ma'am.
your equation, in this case, delta angle S minus beta 1 will be 0, right?
Yes, ma'am.
Okay. So we can apply the same logic and you can check as well. So net change in angle by of this phasor as the tip of the phasor rotates on this close contour will be 0. So delta angle S minus beta 2 will be 0. Delta angle S minus beta 3 will be 0. That means all other, all the zeros and poles of QS which are lying or which are not being enclosed by the closed contour, they will contribute a net change in angle equal to 0. Clear? Is it clear?
Yes, ma'am.
Yes, ma'am.
Now we are left with these phasor where alpha 1 is being enclosed by this contour. So as we'll move along this contour, you see the tip of the vector. The tip of the vector will move like this. Okay? And finally it will come to this. So the tip of the vector, this is the vector, the tip of the vector is rotating like this. Can you follow the cursor?
Yes, ma'am.
Have you understood this?
Yes, ma'am.
So what will be the net change in angle?
Minus 2
Minus
pi
2 pi.
Y minus?
Because clockwise
because it
direction.
is rotating in
Right,
clockwise.
right. Otherwise, the angle contribution by a zero is always positive. But since the tip of the vector or tip of the phasor is rotating in a clockwise direction, right? That's why the net change in angle will be minus 2 pi. So when 1 0 of QS will be enclosed by the S-plane contour, then delta QS will be equal to minus 2 pi only. Okay, clear? Clear?
Yes, ma'am.
Yes, ma'am.
Now what will happen to the QS plane contour, corresponding QS plane contour? So on the QS plane, you see this is my QS vector, isn't it? Or this is one QS vector. Yes or no? I'll have to draw the QS plane vector starting from the origin of the QS plane. Yes or no?
Yes, ma'am.
So suppose this is one QS plane vector. Okay. So now since net change in angle of QS is minus 2 pi, so the tip of the QS plane vector will rotate like this, and in the process it will encircle the origin of the QS plane once in the clockwise direction. I repeat,
No, ma'am. Understood.
clear?
Yes.
So when 1 0 of QS is being enclosed by the S-plane contour, right? On the QS plane, the result will be on the QS plane will get again a closed contour, and the contour will encircle the origin of the QS plane once in a clockwise direction. Now if we assume that two zeros of QS are being enclosed by the sorry, S-plane contour. Two zeros of QS, alpha 1 and alpha 2, are being enclosed by the S-plane contour like this. Right? So we can apply the same logic. So all other zeros and poles of QS plane will contribute a net change in angle which is equal to 0, but because of these two enclosed zeros, now delta QS will be equal to minus 2 pi plus minus 2 pi. Have you understood this? We can construct a vector like this, which is s minus alpha 1, and the tip of the vector will rotate like this on the S-plane contour, thus contributing a net change in angle which is minus 2 pi. Similarly, we can construct the second phasor for the second enclosed zero. So this is the second phasor, and again the tip of the second phasor will rotate like this, thus contributing another angle which is equal to minus 2 pi. Is this clear?
Yes, ma'am.
So delta QS now will be equal to minus 2 into 2, or rather 2 into minus 2 pi, 2 into minus 2 pi, right? So on the QS plane, the corresponding QS plane vector, or rather the tip of the QS plane vector, will encircle the origin of the QS plane twice. You see, this is once, or I can start from here. One encirclement of the origin, second encirclement of the origin. So the QS plane phasor will encircle the origin twice, origin of the QS plane twice in clockwise direction. First encirclement, and then this is the second encirclement. Is it clear? Why? Because now delta angle QS is equal to 2 into minus 2 pi. Have you understood this? Have you understood this?
Yes, ma'am.
Okay. So, applying the same logic, we can generalize this fact and we can say that if z number of zeros of QS are enclosed by the S-plane contour, this is our S-plane contour, which does not pass through any singular point of QS, then the corresponding QS plane contour tau q will encircle the origin of the QS plane z number of times in clockwise direction. Do I have to repeat this? Have you understood, or should I repeat?
Yes, ma'am. Understood.
Okay. Now let us consider a situation where instead of you draw the diagram, let me explain first. So let's take one S-plane contour for a given QS, and obviously the S-plane contour does not pass through any singular point for the given QS, and let us assume instead of one single uh, zero, now the S-plane contour encloses one single pole of QS, while the rest are not being enclosed by this closed contour. So here, instead of this circle, it will be a cross, and instead of alpha 1, we now should write say beta 1. Right? So the S-plane contour is now enclosing one pole of the given QS. Only one single pole of the given QS. Right? Again, we'll traverse along this S-plane contour in clockwise direction. So simply we'll apply the same logic and we'll observe that this phasor, now the phasor will be S minus beta 1. So the tip of this phasor will move along this contour in this manner. Hence, the net change in angle will be equal to minus 2 pi, right? Have you understood this?
Yes, ma'am.
Yes, ma'am.
So the tip of the phasor will undergo a net change in angle which is equal to minus 2 pi. Now let's get back to this equation. What will happen to delta QS? Delta QS. So actually net change in angle of QS phasor. You see, this value is minus 2 pi, right? But since the poles are present in the denominator, hence their angle contribution is negative. So minus, in this case, the net change in angle delta angle QS will be simply minus delta angle S minus beta 1. All these terms will be 0, right?
Yes, ma'am.
So
Yes, ma'am.
now delta QS will become plus 2 pi minus of minus 2 pi, isn't it?
Yes, ma'am.
So delta angle QS will now become plus 2 pi, and hence we'll observe that the QS plane contour will now encircle the origin of the QS plane once in the counterclockwise direction. Why? As delta angle QS is now plus 2 pi, right? Similarly, if only two poles of QS are enclosed by the S-plane contour, then delta angle QS will be equal to 2 into 2 pi, 2 into 2 pi. Hence, the corresponding QS plane contour, just try to follow the cursor, will now encircle the QS origin of the QS plane twice in the counterclockwise direction. Twice in the counterclockwise direction. Have you understood this?
Yes, ma'am.
Again, we are not really interested about the shape of the QS plane contour. It doesn't provide us any information. Similarly, we can generalize this and we can say that if p number of poles, of QS are enclosed by the S-plane contour, then the corresponding, all the conditions remaining same, corresponding QS plane contour tau q will encircle the origin of the QS plane p number of times in anti-clockwise direction. Is it clear?
Yes, ma'am.
Okay. So let's look at one example. Here you see We have taken an S-plane contour which encloses three poles of a given QS and one zero of the given QS, right? So the corresponding QS plane contour will encircle the origin of the QS plane three times in counterclockwise direction and once in clockwise direction. So the net encirclement of the origin, you see for these three poles, three enclosed poles, the net changing angle will be 3 into plus 2 pi, right? And for this single enclosed zero, the net changing angle of this phasor will be minus 2 pi. So again, if we go back to this expression of QS, now this delta angle QS will be minus 2 pi plus 6 pi, which is equal to 4 pi. Have you understood this?
Yes, ma'am. Exactly.
Okay, so that means 2 into 2 pi. That means the corresponding QS plane contour will encircle the origin of the QS plane twice in the counterclockwise direction. So you see, while we'll be plotting the QS plane contour or we'll sketch the QS plane contour for a given S plane contour, the arrow directions are very, very important. So again, we can generalize this and we can say that if P number of poles of QS and Z number of zeros of QS are enclosed by the S-plane contour which does not pass through any singular point for the given S, then the corresponding QS plane contour tau Q will encircle the origin of the QS plane will encircle the origin of the QS plane n number of times in counterclockwise direction where n is equal to p minus z. I repeat, z number of zeros of QS and p number of poles of QS are now enclosed by the S-plane contour, right? So for p number of poles of QS, the corresponding QS plane will encircle the origin of the QS plane p number of times in counterclockwise direction, and for the z number of zeros of QS, enclosed zeros of QS, the corresponding contour on the QS plane will encircle the origin of the QS plane z number of times in clockwise direction. So the net encirclement of the origin of the QS plane is denoted by n, and the net encirclement will be in the counterclockwise direction, and n will be equal to p minus z. Have you understood this?
Yes, ma'am.
Is it absolutely clear?
Yes.
So, what is principle of argument? The relation between enclosure of poles and zeros of QS by S-plane contour and the corresponding enclosure of the of the origin of the QS plane by the QS plane contour tau Q. This relationship is actually known as principle of argument, and will apply principle of argument, or rather we can say that the Nyquist stability criterion completely rests on this principle of argument. Do you have any question? Do you have any question?
No, ma'am.